All right, let's dive in. We're about to go behind the curtain of some serious industrial engineering to look at the incredible unseen science that goes into one of the most important parts of any powerful machine.
So let me start with a question for you. What on earth could a high-tech jet engine, screaming through the sky at 30,000 feet, possibly have in common with a fertilizer factory that's just churning out product on the ground? I mean, they couldn't be more different, could they?
Well, the answer is this little component right here, the industrial shaft. It might not look like much, but it's the unsung hero of the mechanical world. It's the piece that connects everything, transfers all that raw power, and without it, well, neither of those machines would work at all. Simple as that.
And let me tell you, these shafts have what is arguably one of the hardest jobs in all of engineering. They are under this constant, almost unimaginable level of stress. Their whole purpose is to move massive amounts of power every single day without ever breaking down.
So what is it exactly? Well, simply put, it's a rotating piece of metal, or something else, that takes power from point A, say an engine, and delivers it to point B, like a propeller on a ship or a giant mixing blade. But here's the kicker, the really crucial part. Its success or its failure, it all comes down to one single thing, what it's made of.
And it's not like one size fits all here, not even close. Picking the right material is this incredibly complex science. Engineers have this whole palette of options to choose from, and each one has its own unique personality, its own special strengths.
We can basically group them into three big families. First up, you've got your metals, right? Your classic super strong steels and your fancy high-tech titanium alloys. Then you have composites, which is where engineers get creative and combine different materials to make something brand new. And finally, there are advanced polymers. These are specialized plastics and rubbers that are designed for very, very specific jobs.
And the stakes for getting this right, they are incredibly high. This quote right here really nails it. When we're talking about parts where failure is not an option, the selection process is just as intense as it is in aviation. There is zero room for error.
So with that in mind, let's zoom in on the real heavyweights in this world. In high-performance machines, it often comes down to a head-to-head battle between two materials, steel and titanium.
So in one corner, you've got your ASI 1045 steel. Just think of this as the reliable, tough-as-nails, all-purpose standard. It gets the job done. And in the other corner, you have the TC4 titanium alloy. This is the lightweight, high-performance champion. It's famous for that incredible strength-to-weight ratio.
But this is where it gets really interesting, because under the hood, they behave so differently. That term, flow stress sensitivity, that's just a fancy way of saying they bend and warp in completely different ways when you put them under pressure. Temperature is another huge deal. Their strength can totally change depending on how hot or cold it is, and they even react to magnetic fields differently, which, believe it or not, can be a total game changer in certain applications.
But it's not always a showdown between steel and titanium. Sometimes you have a really unique problem that calls for a really specialized and often kind of surprising solution, and that's where the niche specialists come in. So, meet caplalone. This isn't a metal at all, it's a high-strength polymer. You find it in places like the stern bearings on huge ships. That's the part that holds the propeller shaft in place. And yeah, it's chosen because it's strong, but its real superpower is something else entirely.
Its superpower is that number, 0.04. That is its friction coefficient, which is ridiculously low. What that means is that caplalone is incredibly slippery. It just glides. That drastically cuts down on wear and tear, heat, and wasted energy. It's the perfect example of picking a material for one very specific, game-changing reason.
And hey, remember that fertilizer factory from the beginning? Well, the material science here gets even deeper. It's not just about the shaft. Engineers have to know all about the materials the shaft is actually working with. This chart here shows the stiffness for different kinds of fertilizer grains. As you can see, they're all different. The machinery and the shaft driving it has to be designed to handle all these little variations without, shattering the very product it's trying to make.
Okay, so we know what materials are being used, but why are they so strong? To figure that out, we have to zoom in. I mean, way, way in. Because the real secret to all this strength is hidden down at the microscopic level.
To really understand how things break, we have to talk about this concept, plastic strain. Think about stretching a rubber band. You pull it a little, you let go, and it snaps back, right? That's elastic. But if you pull it too far, it gets all stretched out and weak. It won't go back to its original shape. That is plastic strain. And for a steel shaft, that's the beginning of the end.
You can think of this process like a little four-act play. First, stress gets applied. Then, the material enters elastic deformation. It bends, but it can still spring back.
But if you push it too far, it hits plastic strain. That is the point of no return. The damage is permanent, and from there, total failure is pretty much a guarantee.
So really, a material's ability to fight off failure comes down to its microstructure. In hardened steel, for instance, engineers are looking at things like bainite layers, which are like these tightly woven fibers deep inside the metal, and tiny inclusions, which are basically microscopic imperfections that can become weak spots. This is where the real strength, the true character of the material, is actually forged.
And all of this leaves us with one final, pretty cool thought. We've seen how the materials we have today literally define the absolute limits of what our most powerful machines can do. So, the big question is, what's next? What new discoveries in material science are waiting just around the corner? And what incredible new technologies will they make possible tomorrow?